Okay, we now have horizontal collision, meaning I can move the runner horizontally. And the yellow boxes are what I call bricks. That should be pretty self-explanatory. The yellow lines that you see on the runner is the debug lines for the runner collider. Obviously, these things won't be turned on by default when you play the game. These are mostly for me, but you can now see that we can no longer move past the bricks. So I've written my own collision system. I probably shouldn't call it my own. It is a customized collision system. I'm not using what's built in, the Excalibur engine, because like I said before, I want to avoid fractional numbers. I want to go with the whole numbers. So in this case, we should have a perfect collision that stops a player 1 pixel before the brick. So here it is. You might notice something strange here. So there's a pixel here. This is just the rendering part. In terms of pure mathematics, the gameplay itself, we have one integer before the runner's collider versus the brick. This offset happens because when you have a vector, a mathematical vector, that doesn't really have a thickness. When you express that as a single pixel on your monitor, there's many different ways to express it. You could either have it dead center. This is just a very crude example. You could have 1 pixel dead at the center. You could have it on the right side, left side, diagonal. There's many different variables when it comes to rendering, which is why right now I'm not deciding to do anything about this. It has nothing to do with the gameplay. It's just a rasterization mismatch, which I might get deeper in another video, but for now, just want to show you that we have a working horizontal collision system. So let me talk slightly more about the custom collision. I have unsigned integers, an array of unsigned integers, which are 8 bits. What does that mean? It means I have individual cells, which match the grid right here. I have these cells that fill up your entire level. And when you register a brick to the level, we register whether a certain cell is filled or not filled. In this case, it's a very simple 8-bit number, 0 or 1. 0 means the space is empty. 1 is there's something solid there, therefore you cannot go through. The smallest unit for the grid, as well as the solid unsigned integers, these unsigned integers that represent the solid area, they're all 8 by 8. Right now, the brick is, I think this is 16 by 16. So possibly I could have a brick that's the smallest, which is 8 by 8. Right now I'm just settling down on 16 by 16. So based on the level design, I look at each of the bricks. I could have other objects as well, but in this case, it's just the bricks. There's an array. Let's see here. This is a solidgrid.ts. There's an array of unsigned integers that represent your entire level. You might worry that the array might be too big. That's not an issue because 8 bits is, I believe, the smallest unit in JavaScript. It's practically nothing. The only reason I don't have something like a single bit arrays because it's not worth going through the trouble of making it. It's just not supported. People are good with, I think most people are good with 8 bits being the smallest unit in JavaScript natively. And checking whether a number is 0 or 1 running through the entire array, which is contiguous memory, it's not going to put too much strain on your machine for the most part. And the entire game resolution is 640 by 360. A level could be a few times bigger than that. Still, it's not a big deal for most modern machines. So if you try to debug it, a level might look like a bunch of zeros, and any area that has a solid object in it will be marked as 1. So if you have a brick that's 16 by 16, you might have something that look like this. So 1 represents a filled area, and every time the runner moves, we check whether the area is filled or not, and then we decide whether the runner can move in that direction. And we're not even checking the entire level, we're only checking when the runner is moving. We have something called the move buffer. Let's see where it is. Move buffer resolve. So when we have a state, when we have a runner state, something like run, this state itself does not directly move the runner. Instead, what we do is we show the intent that the runner is going to move. So in this case, we have something called a horizontal move buffer. We put a number into that buffer. So if you're moving to the right side, you would have, for example, a move buffer of 8, which means in that frame, the player is about to move 8 integers into the right. Now the buffer is there because first we get the buffer and we look at whether the area that the area where we're about to move has a brick or not. If we have a brick there, then obviously we stop the runner right before the brick instead of going through it. If the space is empty, if the space is all full of zeros, then we don't have any problem moving. So that's the entire horizontal collision. It's all made up of integers and straight lines. So generally, we do have the concept of AABB collision, but it's a much more simplified version specifically for this game. It should be a lot faster than running through a generalized physics simulation. I haven't actually looked at the Excalibur physics, just because I stopped when I realized that it's based on floating point numbers, and I didn't want to deal with floating point inaccuracy, so I just ditched it and went with my simple custom integer-based collision system. I don't think I'm going to talk about all these topics in this video. I don't want to get too much into the details. So I'll just talk about this part. This is an interesting topic. Shrink the bottom by 2 to avoid floor collision. This means that we can see that the runner is right on the floor right here. If we don't actually shrink the runner's vertical collider by 1 or 2, this counts as a collision, and this player's going to get stuck on the floor and won't be able to move. This is one of the classic problems with I should say old school platformers. And there's many different ways, like skinning. In my case, forcing the player and the brick to have at least 2 pixels intersecting to count as an actual collision. There's simple ways around that, so there's nothing too complex here. It's mostly straight lines and checking whether a space is 0 or 1. That's pretty much this entire collision system in a nutshell. So for next video, I should finally have vertical movement. And when you have vertical movement, I should also have jumping, gravity, collision with the floor, and so on. So that's it for today. Thanks for watching. See you next time.